സാറേ സാറേ ഇതല്ലേ പുള്ളിയല്ലേ ഇതല്ലേ
അല്ലല്ല ജോസഫ് സുരേഷ് ഫയർമാൻ അവിടെ തന്നെ പ്രൊജക്ട് ചെയ്യും.
ഇതല്ലേ ഇതില് മറ്റേ മീറ്റിൽ ജോയിൻ ചെയ്ത് ഏതെങ്കിലും എടുത്തിട്ടുണ്ടോ മീറ്റ്
എടുത്തിട്ടുണ്ടല്ലോ.
ഇതായിരിക്കും ഇതാണോ
ഇതല്ല സാറേ
ഇതല്ലേ
Morning. I'm audible.
ഒന്ന് റിപ്ലൈ ചെയ്യാൻ
Hello, Praveen. Yeah, hello, Dr. Susha. Yes. We'll start in 5 minutes, sir. All right. Oh, I'm audible, correct? Okay. Yeah, yes, audible. Okay, great. Thank you.
ഇതല്ലേ അക്ഷയത്തെ ഇതല്ലേ ഏത് മാത്രം കിടക്കുന്നുണ്ടല്ലോ തൽക്കാലം വേണ്ടല്ലോ
എന്താണ് മ്യൂസിക് വെച്ചത് ഇതല്ല ഇതെന്താ വെച്ചത് സ്റ്റോപ്പ് ചെയ്തു സ്റ്റാർട്ട് ചെയ്തു അവർക്ക് കേൾക്കൂല അങ്ങോട്ട് കേൾക്കൂല ഓക്കെ
I hope everyone is energized with the after having the tea. So let's get started with our plenary session. A brief introduction of our plenary speaker. Fabian Suvija is the Technical Director of International IoT Communication Technology, GmbH IICT. Currently, he's leading the IoT communication testbed development with diverse leading technology partners in Germany, with a focus on international market requirements around IoT and use cases of next-generation wireless technologies. He has masters in industrial automation and mechatronic systems with Southwest Germany and has multiple years of experience in research and industrial projects with a focus on testing, integration of cellular Internet of Things and low-power wide area network solutions. I invite Fabian Suvija to deliver his plenary session.
Yeah, thank you very much. I hope I'm audible and that you can see my screen. Okay, great. Then thank you for the introduction, and I'm happy to speak here in this plenary session. So as already introduced, I'm basically now joining virtually from Germany on behalf of IICT. And I want to give you today an overview of an industrial perspective on how 5G is revolutionizing IoT. Yeah, so my topic today is revolutionizing IoT with 5G innovations and future prospects. So I will give here a comprehensive overview on how 5G is driving, specifically in the industrial IoT field. So I will talk about some of the core innovations, some use cases and projects we are executing in that domain, but also about some research aspects. And of course, in the end, I will also give an outlook towards future innovations and also the future prospects that we can expect with 5G, also towards the 6G technologies. So I structured this talk to start with a short introduction into IICT, what we are doing, to give you a little bit of context before I talk about 5G essentials in IoT. So how does 5G fit in IoT? Before I will talk about the 5G innovations, so specifically from an industry perspective point of view. And then I will talk about testing and evaluation of 5G-based IoT solutions. So where we did a lot of research on different unified methodologies, testing methodologies to create very comparative and reproducible test results. And last but not least, I will give you an outlook about the future directions. Yeah, so let's get started. An introduction to IICT. So We are International IoT Communication Technologies. We are a Germany-based, privately held company, and we are working basically in various fields related to embedded systems and communication electronics, which spans from technologies in cellular IoT, as my talk is today about 5G, for instance, but we also work in the fields of low-power wide area networks. There you might have heard, of course, of LoRaWAN, but also newest technologies such as MyIoT that bring in new innovations specifically for low-power networks. And then, of course, from an industry point of view, also from a German point of view, we have lots of different industrial applications, industrial protocols, where we now see there's also this bridge between wireless and industrial, getting feasible also specifically with technologies such as 5G, where we also strongly focus on. And then, of course, we can also see AI coming to the embedded systems, which is also our expertise area. And we are then basically, on the one hand side, using these technologies, doing research on these technologies, and also implementing different use cases. So as you can see here, just with these technologies that are outlined here, many different use cases can be implemented and can be achieved. So at IICT, we are, as I said, working on these different technologies. On the one hand side, to build testbeds. Testbeds, as you see, for example, here, are basically experimentation environments that can be used for projects, for research, and for training. So where we basically combine different infrastructure elements, such as different wireless technologies, 5G infrastructure, for instance, as you can see here, 5G core, plus a software abstraction layer, which makes it easy to get into research, project execution, and training. Yeah, as you see, the next pillar is here training, where we also have various activities also in India, where we focus now on the hands-on training aspect. So with the different technologies I outlined before, we focus on creating curriculums or trainings that really enable learners to work on different use cases and different technologies on hardware as well, as you can see here. And last but not least, we are working with different companies together on the one hand side to drive research forward, but also to implement new use cases or implement use cases for different companies. So this just as a high overview of what we are doing and also where we are coming from. And now I will give you an overview of 5G in the IoT domain and then how this is useful and also what kind of research we are doing in that field. Yeah, so I'm sure you all know the term Internet of Things. So the interconnection of devices that communicate over a network with the goal to basically work on data, so collect, process, and act on the data. But we basically can see this, of course, one can use different layers, but typically at least 5 layers, from perception over transport to processing, application, and business logic. All these things are, of course, implemented typically also on different elements. For example, here we have sensors and embedded systems. Here we have wireless networks. Here we have typically an edge cloud, and here typically a cloud and user application. So we now, in this talk, specifically focus on the transport layer, where, of course, we can see different wireless technologies being really the enabler here. You can think of LoRaWAN, you can think of 5G, NB-IoT, different technologies that enable the IoT. And of course, why this is so important is because connectivity is here oftentimes the main influencer of KPIs. For instance, the power that I need will be mostly mandated by the transport that I'm using on the end device. Also, the cost will be highly mandated by this transport layer because the sensors in IoT devices typically are nowadays already rather affordable. And the other things are scalability and reliability. Of course, specifically when talking about industrial, the reliability gets also more significance. So in the end, we can conclude that the choice of connectivity here of this transport layer dictates the KPIs of an IoT application, and therefore is one of the most important parts, even though, of course, all the parts are necessary. So just to highlight that as well, if we look now from the industry perspective, looking at different requirements, let's say, for example, we look here at a discrete manufacturing use case. For instance, here, motion control. So this could be some kind of robotic control system where we talk about latencies of 250 microseconds to 1 millisecond. So this is typically something where we still use cable-based communication, just because we need, on the one hand side, low latency, but also we need a very high reliability, and also we need a deterministic latency oftentimes. Whereas you see energy efficiency here is not really that important. However, if I look at process automation, oftentimes latency is not really a factor. We oftentimes, it's sufficient if it just arrives at some point. And what we can see here, however, is energy efficiency, for instance, is here, for instance, 10 years. So that's, of course, a huge difference with regards what requirements are needed for different use cases, specifically from an industrial point of view. And this is where wireless still has different challenges, where there are, of course, different research and developments that bring the wireless domains also into scenarios such as this one over there, because we can see that still we have this kind of mobility necessity, for example, in AGVs, or we have the scalability necessity where the wireless IoT assists a lot also in enabling these new scenarios. So basically, to summarize, we have a lot of different use cases that could benefit from wireless IoT in general. So just think of, for instance, smart city, where you need easy installations, you need high scalability and long battery lifetime. Whereas, as we just saw in factory automation, we might not need the large scalability or large range, but we need deterministic latency, for instance. But still in industry, we want also to have the flexibility. Like if you think of industry 4.0 and 5.0, we want to have the flexibility to have adaptive production streets, for instance, or we want to have mobility scenarios. So the requirements are really much different, and that's why the technology landscape is very diverse and also very complex, one can say. On the one hand side, of course, various different standards, cable-based, wireless-based, and also much different focus groups. For example, MIOT or LoRaWAN will not be suitable for a factory automation use case, whereas TSN will not be achievable to implement over IoT, at least not fully. So this is where we see 5G coming into that IoT, wireless IoT landscape, because with 5G and also 6G, we not only consider one specific use case domain, as these technologies typically do, but we consider various use case domains, specifically also from an industrial point of view. It's already in the standard, basically, that it should focus on these industrial use cases. And in that way, we see it as a revolutionizing technology here. Of course, this is also an ongoing process, but overall, with the goals are defined, with the standards that are being defined, this is definitely revolutionizing the wireless IoT, because with one technology, we could cover multiple use cases. We can have such heterogeneous scenarios. Yeah, and as you might know, just a very basic of 5G is this application triangle, which was already defined very early on. So these are the 3 pillars 5G focuses on. This is enhanced mobile broadband, meaning it gives you higher internet speed. This is important for your usage of your smartphone, for instance, where you now can use new internet services, but also streaming services, for instance, and so on. On the other side, what is more interesting from an industrial point of view are ultra-reliable low-latency communications, where you see something like the industrial automation coming in, like the robotic control, mission-critical applications, and also self-driving cars, for instance. That could be all possibilities. And on the other side, 5G also focus on massive machine-type communications, meaning large-scale networks with low power requirements. And these requirements are really very much distinct, and 5G also has, of course, the physical limitations of other wireless IoT solutions. However, it offers a huge configuration potential, and this is something which I will also cover now. So when we talk about 5G innovations from an industry perspective, where do we see 5G being very helpful? So it's now for us, it's not really about the high data speed that we want, which is typically interesting for an end user, but we are rather interested in deterministic latency or low power, for instance. Yeah, as an overview, key innovations from an industry point of view, definitely from a German perspective, it's definitely campus networks. Campus networks are basically non-public networks, meaning I do not depend on the cell towers that are deployed by the operators, but I can actually deploy my own 5G network. And this is the point that I mentioned before. Now we get the whole network under our own control. We can configure it to our own need, which only now makes it possible to adjust it to a scenario that we deploy into our company. Then we have things like an enhanced quality of service model. Also, I will talk about that in a moment. And flexible networks, meaning we have network virtualization, we have network slicing, which allows you to run these heterogeneous scenarios, as you can see here. Basically, we can define such different slices depending on the use case. If we have this factory automation use case with lowest latencies, we can define such as logical slice, which is configured specifically for that use case. If you have another use case like a condition monitoring use case with low power requirements, we can configure the slice with that necessary configuration. And this is just something that in a public network, the operator controls that. So we oftentimes do not have an impact on that, and we just need to use whatever configuration they send us. So as you might have experienced with your smartphone, if you're connected to the mobile over 5G, for instance, your battery will drain much quicker. But that is also the case because of the operator settings, because you want a certain quality of service, you want the high data speeds, you want to be reachable. That's why the settings are as they are, and that's why they drain the battery. But for an industry point of view, we want to have more flexibility here. And of course, there are also the points as open standards, so we can use many more different hardware vendors. The architecture is much more open, which also brought up many open source tools, for instance. And then, of course, there's a lot of innovations on the radio access network, which I now will also not go over in detail. So just to outline the 5G architecture, you all know the end devices, which can be smartphones, but since we also go into the industrial domain, these are typically modems such as that one, which are then integrated into different circuits. There are already different commercial industrial applications also available. And then we have our radio access network, which is now more modular, which allows for more vendors to be active in that field. Also, the interfaces are more open and standardized. And then we have the 5G core, which runs completely as a software component. And there is also a huge update there from the legacy cellular systems like 3G, 4G. This is now following more modern software standards, you can say more modular approaches. So one can, I would say it enables more people to work in that domain as well. And when we talk about campus networks, a campus network could look as simple as this here, where basically here we have our 5G RAN. So combining these three elements that I showed before, our 5G core is now even able to run on such a small mini PC. And then we have our end device, which could here be, for example, such a USB dongle, which we can place into our laptop with our own programmed SIM card and then have the 5G connectivity. So there you can see this already looks a little bit more like a Wi-Fi network. However, you have some of the benefits of 5G where Wi-Fi is lacking, for instance. So this is, at least for the German industry, this is the biggest innovation. I would say that these campus networks opened up with their own dedicated spectrum that we can use, which also many industries are nowadays already using here. And just to give you an overview, in India, this is also still basically under development, let's say. But basically, we have different deployment scenarios. That means we can either, for example, use it completely on our own premises. That means we are completely responsible for our network. We are completely responsible to configure it, to maintain it, which is, of course, useful if you want to really have full control. But sometimes you also want to make use of the public network. That is, of course, also a very valuable resource. The networks are deployed, they are there, they have the cell towers with the high power. So we can have also such integrated scenarios like a shared RAN, for instance. That means we can have this integration of our local services here. For example, we want all our user data to be within our company, but we want to use the radio access network of the public partly. So this is also a possibility that we can do. And we can even use parts of the core networks. As I said, the core is just something that is typically run by the operator, just a software component. And we might even just use parts of that software component because of that modular design. For instance, I could say all the user data stays within me, but the rest of the core services, like for example, the authentication services and these sort of things, they can be still handled by the operators. So I have here a minimal setup. For me to get started with 5G, I can use some public infrastructure, I can use a public core, but I still keep all the user data within my premises, which makes it more easy to manage, more easy to set up. However, I also get a bit less flexibility. So just to showcase, you don't have to handle all yourself. There are different possible scenarios. So how did we use that in the past? One example here is a use case for process automation, where you can think of a chemical industry, for instance, that uses these valves. So these are huge valves. They are actually a couple of meters in size, and they control the liquid flow in the big chemical process automation factories, for instance. And here the use case was to control them or to retrofit them with a wireless sensor. So in that case, it was still NB-IoT, which is now part of 5G as well. But we basically looked into how we can integrate that into the system to make some predictive maintenance use case possible. So to track, for example, the flow of gas, the flow of liquid, and also the pressure of the liquid completely wirelessly. And here in that research project, we could also find out which would be the parameters or the configuration that one needs to configure to achieve these requirements of that use case, which was, of course, a high reliability. Latency was not that important. However, energy efficiency was also very important, where there's, of course, most of the challenges were with regards to the configuration of the network and also optimization, for instance, of the signal strength or of the reliability in that scenario, where we used also, for instance, an antenna array. On the other side, when we talk about this ultra reliable low latency communication, we had here a use case together with Airbus, for instance, who are having, of course, these huge factory automation, these huge halls where they manufacture the planes, and they have different AGVs, they have different control systems. So a lot of industrial protocols such as Profinet are being used. However, they want to explore also how to make the manufacturing process here more flexible, have the flexible setups, having the AGVs. So where they're interested in wireless IoT and where these campus networks come into play is basically because with 5G, they could cover these requirements of Profinet, which is a deterministic low latency and Ethernet-based protocol, And our job here was basically also to integrate or to create these Profinet 5G bridges for these operational technologies. So I'm coming also to that a bit more now. So if you think of latency, why is it important? So just here some demonstration, a simple task, just catch the ball. But here we have an artificially introduced latency of 40 milliseconds. So this is something that you have, for instance, in an LTE network. As you can see, this simple task, all the participants are not able to solve it just with this seemingly small latency of 40 milliseconds. It's not possible. And in 5G, we have now latencies down to the millisecond. And this is basically also this critical range that makes it attractive for these industrial applications. But latency is not everything. There's also the deterministic communication. General motivation here into this kind of deterministic communication or time-sensitive networking is here that we have now campus networks. We want to use them for industrial applications, for instance, like AGVs, but we need to have the deterministic latency. So we need some kind of additions into that. So what do I mean with deterministic latency? It basically means the right packet should arrive at the right time. So we don't want to have any congestion loss. For instance, if you have a lot of applications sending, like your streaming application and your factory automation communication, you want the factory automation communication to always arrive at a certain bounded latency. This is what we can basically see here. If we have this loss probability here on that axis and the buffers allocated on that axis, we can see we don't want something like this, where we have these end-to-end latencies with these tails, which would basically mean, okay, most of the time packets would arrive in that time, but sometimes we still have these outliers. They are not acceptable for these use cases. What we, however, want is to have this kind of hard barrier. So we want nothing to arrive after that latency, and the system must ensure that this is true. And this is what TSN is basically all about, and what was also that project about, to create these Profinet bridges to allow this kind of deterministic latency. And TSN basically is a big standard, or it combines multiple substandards. One crucial thing here is time synchronization. So if we talk now about a network, a 5G network, there are multiple components. They should all have the same time. So we have a base station, we have a core, we have multiple end devices. They all need to have the same time to also know when is that bounded latency. We have traffic shaping. That is the scenario I just talked about. If we have a streaming application, if we have a factory automation use case all going over the same network, we need to have some kind of mechanism to treat the traffic differently. So not all traffic is treated equally. So we have different traffic classes, we have different QoS levels, and we have a shaper, which basically says when which packet is going to be sent. Then also we have redundancy and we have some configuration. However, these are now not that important for that talk. And what we did then in that project is to develop a prototype implementation here. Of course, these are now standards, that this is already under standardization. However, the implementations are still behind. So where we worked closely with the TSN specification here and also with different 5G domains. So on the one hand side, you can see here a virtual setup. So you run as a UE simulator, an end device simulator. We have also our 5G core, and we have here the different necessary TSN components integrated. And in the end, we have here also a demonstrator created that works completely with commercial elements, such as a Quectel modem. We have an Amarisoft 5G core, and we have different translator bridges, which were then created by us to then achieve, for instance, here this slave sync accuracy of 150 nanoseconds, which is already a good achievement, where we are still working to bring in other elements of TSN here into 5G. And of course, there are different challenges of how that can be done. Yeah, and this just outlines some of the, let's say, research and development steps in the TSN direction. Of course, this is a complex topic where multiple different standards have to be looked at, also different commercial modules and the integration into 5G, so how these things fit together. However, as you can see just in that outline, it was possible to create it and also create then this Profinet over 5G use case. Yeah, one big topic that we at IICT are also looking at is testing and evaluation, which is of course a crucial step. Even in the scenario before, of course, we always need to get some measurements. We need to verify the system. And specifically for us, it's also interesting to compare different technologies. So one problem that in general we see is that for testing, we always need to have it very systematic, reproducible, and we typically also need it throughout the development cycle of a product. So if you now think about 5G, as I talked about before with TSN, this is something that is mostly just under specification, or 6G now. So there we might have already some simulation models because these things are already specified, but we don't have hardware available yet. So this is typically something where we can start with in the product development cycle or in the technology life cycle. Then on the other side, of course, once the devices are there, we can do field tests. However, field tests, they are very expensive because you need to have the people that go out to the test locations, they perform the tests. Then whenever you have some changing occasions, like there might be some obstacles in between your wireless link, the test results might look already much different. That's why for us it's important, what we also created in that research project here, was this emulation layer in between, which basically emulates these channel conditions in a reproducible, fully automatable way. And that project focused now on creating a test system which allows to use the same test case, so test case description here, to run now on the different layers. So we run first simulation, then we run in an emulation, and then we run in the field. And then we compare also these results. So of course, simulation always has some abstraction, at least on the physical layer. These here also abstracts already certain things, but we are using already real devices, but abstract the wireless channel. And this allows us to really do systematic testing much more efficiently, fully automated and reproducible. But last but not least, we always need the field verification. This is basically our baseline to then compare how well do these environments abstract and how well does, for example, this emulation layer work for our lab testing. And this is what you can see here, just with a couple of elements. For example, here, this is our emulated test bed. This is a typical field test scenario. And I will now just give you a short overview into that. So this is what we mostly use for our lab tests, because in this network here, we have different shielded boxes where we can include our wireless end devices and base stations and so on. And on the backside, you can see this kind of network, which contains of different RF elements, such as attenuators, multipath lines, and so on, which can then create various scenarios. For instance, you could say, increase the distance step by step. For example, here we can increase the attenuation step by step, or we could even say close the connection between node 7 and node 8 suddenly and see how well the network performs with that connection loss, how long does it take to again take the connection, and things like that. And of course, being able to fully automate that allows us to test various different scenarios. So here I just want to outline one specific test test case that we were running, where we basically wanted to have these reference measurements, so we tested in the field. Then we characterized that field environment by using values such as the SNRs, the RSRP measured, and then we recreated that in our lab scenario here and in our simulation environment. And then we wanted to compare how do these environments compare to each other. So this is, for example, what we can see here. Our setup was now to set the RSRP in the APTP, so in our emulation testbed, to the median RSRP that we measured in the field. And what we could see here as a general observation is that the SNR was now slightly higher in the APTP. Of course, there was still a bit less noise, we can say, for all our technologies that we've used. And we had also less variance in the APTP. However, the overall results that we could achieve in the APTP were very realistic. For example, if we also looked at the latency, this was very much comparable as opposed to when we were testing in simulation environments. The results differed greatly because we did not have, the abstraction was just much more. We did not have the real devices. And this is how we basically verified, okay, this environment is suitable. However, it's not fully realistic, of course. If we go to the field, we will typically always have some kind of wireless conditions which we cannot fully model yet. And in the end, we also use this automated testing approach to find optimized configuration. And that is something that is now very crucial in 5G, as I outlined before. We have a huge configuration potential, and only with that configuration potential, we can make use of these different use cases. So here we performed an extensive measurement campaign going through various different parameters of the 5G network. So it was a very high parameter space as well. And the testing was only possible because we had these emulated labs. So we used real devices, an emulated lab, and tested with various technologies. And in the end, the goal was here to give guidelines for a technology selection, for instance. So what we saw, for example, which parameters had a huge impact or not so much impact, which is outlined basically here. For instance, for NB-IoT, we can see all the different parameters that we were varying here. For LTE, LoRa, and MIOT as well, where we can basically see which parameter has the most impact on a certain KPI. So just here, looking at latency, looking at range, and looking also at energy. And then we could outline, okay, these are really the features, for example, from an industry or from an applicant's point of view, which are the parameters one should really look at if one is interested, for instance, in energy. Here look into the PSM feature, and then we can also give more insight into how to configure that. Or if we look at LoRa, for example, of course, it's rather the SF and the repetitions rather than only packet size, TX power, or acknowledgements, for instance. And these are some of the findings out of that project. And this is also where our testbeds basically come in, where we can create such automated test cases to find out suitable parameter sets for a certain given use case. And just to give you an overview for an educational point of view as well. So here is a small testbed demonstration where we can select different technologies here, for instance. Via this UI, we can set the parameters. So this abstracts various things here, like how to configure the end device, how to configure the network, how to optimize for that. And then we can run, for instance, here different use cases. This is now just exemplary for the My Connected Garden use case, which just transmits different sensor values over LoRaWAN. But it could be also, it's also sent over MIOT. And in that way, we can now, for instance, just compare which of the technology performs better for a given use case. These were now a lot of topics. But I want to last but not least also give you some future directions of what we can expect from 5G. Of course, 5G is basically updated incrementally. We have the different releases, the release schedule that is defined by the standardization organization. and it's already clearly defined when we will see a new release, and it's also defined which will be the topics that will be worked on in all of the releases. So release 17, this is already out for some time. However, I still included it here because even though you might see here release 18 being finalized here in 2024, until we see that coming into the implementation into the end devices and fully supported, that will still take a couple of years. So these changes that we see here in release 17 and 18, this is something that we will just see in the next years. So here, of course, in release 17, very importantly, we have these reduced capability devices. So this is something specifically from an IoT perspective interesting, because these reduced capability devices, as the name implies, they are now not fully capable of everything your 5G smartphone modem might be capable of, and they are optimized for low battery power, a lower cost, for instance, and they are typically optimized for these small data transmissions. So basically making it more affordable and tailor it more for the IoT use cases, because here we don't need these huge bandwidth. Then, of course, non-terrestrial networks. This is something that is also coming up. So integrating the terrestrial 5G network that we currently have with also satellite communication. So this interworking of satellite or non-terrestrial and terrestrial networks is something that we can also expect from the cellular communication. And this, of course, will enable a lot of new use cases, which we can already see with some other non-terrestrial network technologies being achieved, for instance, in agriculture, or just giving the connectivity to locations that are a bit more remote. Then we have different side link enhancements. So, for example, device-to-device communication. And of course, as I also outlined, this TSN integration. What we saw before, this is something that works now in the lab, that we have also achieved a Profinet over, but to have that commercially available will be, of course, also huge for the industry, specifically here with all the discrete manufacturing use cases. But this is also something that we can still expect in the next years. And then, of course, in release 18, just to highlight a very little amount, basically AI/ML is also coming in. So this is coming in mostly on the network side, on the RAN side. So how to manage these resources more efficiently. So of course, currently there are also different algorithms into that, but of course we can also make use of ML algorithms to optimize the resource allocation and the energy demand. And in that way, the whole perspective is also to get into more sustainable networks, which is also outlined here as one of my last slides now in these IMT 2030 specification, you can maybe call it. So this basically defines what 6G should be able to do. So here we see our application triangle of 5G. So that was in IMT 2020. And now in 6G, what comes in newly is AI and communication, ubiquitous connectivity, and integrated sensing and communication. These are some of the new pillars, which of course are very exciting. But of course, these domains that we worked on before, eMPP, MMTC, URLLC, they will be renamed, basically, you can say it, and they will be worked on more, because right now what we can also see, they are defined, they are specified, there are goals, but we are still far from having everything achieved here. So from an industry point of view, for us it's interesting, again, working with campus networks, so these private networks, basically, we want energy and cost efficiency, we want dependability, and also use cases such as high precision and heterogeneous scenarios are something that, from an industry perspective, is very interesting. And as I said, 5G has not yet reached its potential, so it's really undergoing a lot of different specification. And since this targets that many use cases, this is a long process. So while working on 6G, all these things that are initially targeted also for 5G, they will continue to improve, and then we can only see the full potential also of 5G. And where we, of course, also see that the deployments in 5G, specifically in the industrial context, they will also still grow more and more. And then as a last step, how are we now going forward with 6G at IICT? So we are always interested in looking not only in one technology, but having multiple technologies considered. Even though 5G tries to target all these use cases, we still want to have a very transparent overview of how to work with different technologies together. And we still think that multiple technologies need to work together. So to have this kind of interoperability is one of our core topics here. So what we are aiming, we are now also creating a new test beds, of course. So here you see a multi-IoT XG test bed, meaning we support multiple IoT technologies also towards the next generation mobile networks such as 6G. And we want to be able to basically compare these different technologies, different vendors in a unified way, where we work on this technology abstraction layer to then in the end be also able to enable different use cases and enable also users to optimize their use cases, where we work here on different network optimization techniques and also this environmental configuration for our testbed, which we can still further advance. So basically, we are working on scalable and modular infrastructures, the AI and ML-based optimization, and integrating these new features all into a testbed to make it also possible for different stakeholders, be it industry or be it academia, to make use of such a testbed to really work with the newest technologies, and in that way also enhance their capabilities in research, but also in projects, and also drive the technological innovation with new use cases. So this is what we see as our next focus points. And of course, the technology domain is evolving fast, and with always these new exciting achievements. So we are also aiming to integrate those things always directly into our testbeds. So this brings us now already to the end of this plenary session talk. And I'm also open now, of course, for questions from the audience. I hope that you got an understanding into this industrial IoT perspective, specifically how 5G can fit in, how it can be useful, and also which are still some of the challenges, which are some of the prospects, but also that you see there is a huge potential to work, of course, also in 5G itself. Thank you very much. And if there are now any questions, I'm free to also answer them.
Thank you, sir, for the session. Can we have some questions from the audience, please? Does anybody have any question? Nobody? So let me ask you a question, sir. When 4G was introduced, it created a visible boom in usage and impact. However, with 5G, the shift hasn't felt as evident as 4G to the public. So what do you think are the reasons behind that? And how are such challenges being addressed? Also, especially since the decisions around 6G have already begun, how are you going about it? I hope
thank you for the question. Of course, on one side, 4G, that's true. That's for the public, got much more impact, I would say. Mainly also because 4G was mostly still targeted at this kind of audience. So at the audience of end users. So where we really wanted to have the increase in speed, right? That's really what you saw also from 3G to 4G. The speed or the bandwidth increasement was huge. You got a huge benefit out of that. And in 5G, the core focus was, even though one of the focus points was also the end user, the core focus, however, was more on these industrial applications, and to make it, there was a lot of specification work going on in making the interfaces more open. for instance, using the SPI-based interface in the core itself to also make the RAN more modular, offering their different interfaces, different standards. Then focusing much more on the industrial use cases and the IoT use cases, which, on the one hand side, they are not that visible to the public, I would say, specifically when working in the industry. And on the IoT side, there are still some shortcomings. So 5G coming completely from that cellular domain, the requirements are just much different. For example, the energy consumption is still a big issue in 5G, where it's not yet fully suitable for IoT, which is one of the reasons why you don't see that much deployed yet in IoT. So I would say these different points together made it look less impactful. However, at least here, when you are coming more from the industrial side of these campus networks that I also mentioned, these created quite an impact here, and also quite a fuss and a lot of implementations in Germany. This was really having a big impact here. Whereas from a user point of view, I agree that it might not have felt much, also because the data rates that we can now achieve, this might be not really visible in your day-to-day application. So if you just use WhatsApp, maybe even doing some video calling, that is also fine over 4G, where you rather just need to make sure you have a good connectivity, and the data speeds in 4G would be typically sufficient. So these advancements also with regards to millimeter waves, which you might know. So these huge data speeds, this is something that has not even been deployed in many cities, and typically you don't have the long range. So this is something that, these are some of the points I would say that lead to a felt that you might feel it's a bit less significant than maybe the 4G improvements. However, what I also see when looking to the future, they now paved also the way with these new architectures, and with focusing on these different domains, they basically paved the way for further innovation, and where you will also see it in IoT, in non-terrestrial networks. And so there will be definitely all together, if you combine all the different domains where 5G and 6G will be active, you will see more impact if you combine all that together, but maybe not so much in the user domain anymore. I hope that answered your question.
Sure, sir. Thank you for that. Any more questions?
Good afternoon, sir. So, about this multiple IoT, how much latency you are expecting? That is one point I want to clarify. Another one is, if you want to implement this multiple IoT, if 3GPP standards are sufficient, or we have to move from 3GPP and to some other new standard. That's what.
Thank you. So when I talk about these multi-IoT, so typically, with multi-IoT, so we want to compare here different wireless technologies. So there could be, on the LPWAN side, for instance, LoRaWAN, it could be MIOT. They have typically latencies in the range from a couple of 100 milliseconds to a couple of seconds to even tens of seconds. So that is the latencies that we talk about here. If we talk about BLE or Wi-Fi, of course, we can be also in the range of tens to hundreds of milliseconds, but specifically some 5G use cases that are now relevant also for us. For instance, these industrial automation use cases, they typically require sub 10 milliseconds or even sub 1 millisecond latencies. So this is something specifically where, when I talked about these TSN and Profinet communication, so these standards that we try to bridge there, for instance, with this Profinet 5G bridge, Profinet itself just requires a very, I think it's a 10 milliseconds raster that it requires. So of course we need to have the 10 milliseconds boundary of 5G. But there are other technologies that are also highly used, which have the 1 millisecond raster, where we are looking at latencies of 1 millisecond. And altogether, the 3GPP specifications, they are very, very broad, I would say, and oftentimes sufficient, I would say. However, the implementation is oftentimes also behind. What we even see now in commercial modems, even if they say they support release 18, they pick certain things that they support and certain things that they do not support. Where I rather see also some of the manufacturers that are simply not working on completely implementing the 3GPP specifications, I would say. But altogether, these gremiums that are together there, and I mean, it's not only 3GPP there, right? I mean, there's different, even industry gremiums. From German side, there is the 5G ASIA, for instance, that gives there a lot of input in what are really the industrial needs. So it's a big ecosystem, I would say, where people from different domains try to also give input to 3GPP, different people working into that specifications. I would say that this process is good. But also in the implementation phase, this needs to be more strictly implemented. Where it was a bit frustrating sometimes also from a research perspective, where you see, okay, there are some release 18 modems they support already, for example. In that case, we need some Ethernet PDU sessions or so. However, then you get the modem and you notice that this is not really supported. Yeah, I hope that also answered your question.
Do we have any more questions? I hope there are no more questions. Thank you, sir, for the insightful session on the powerful convergence of 5G and IoT in shaping the future of industrial innovation. Your clarity on private networks, TSN, and testing strategies truly broadened our understanding on next-gen IoT. We are grateful for your time and expertise.
Yeah, thank you very much for having me, joining here virtually, and I hope you have a nice rest of the conference. Thank you very much.
Thank you, sir.
Goodbye.
Hello? Hello? Right. Hello, am I audible? Am I audible? Okay, well, I think it's time for us to start this plenary talk. Well, from what I've seen from the overall perspective of this conference, although there is a, you know, uh, emphasis on electronics, communication, etc., it's somewhat unfortunate that I had to fit something on neuroimaging, which I have been working on from my research perspective. Through my academic research, I was all along focused on neuroimaging, several clinical aspects, and which involves a lot of computational signal processing, image processing. That's where the convergence comes in with the curriculum of the BTech electronics and communication students. So what I'm going to talk about today is mostly on brain aging to start with, the fundamental ideas. So I would just, what shall I say? Because I'm talking to BTech students mostly, rather than advanced professional people. So I would like to sort of slant my talk more towards as a tutorial and interactive conversation, rather than just flooding through all the slides and get you people bored, especially the young students sitting behind. So when I say brain aging, it doesn't mean your age, when you were born. So I would say, I'm 60 years or somebody is 40 years. That's not what brain age means here, first of all. So that is why there is this keyword decoding. So we all know what is decoding, isn't it? So if something is coded, we have to decode it. Am I right? And of course, nowadays, AI has become a machinery for that purpose. Although, when I was a student, when I was doing research, there was not much of AI. Everybody used to talk about pattern recognition, and intelligent expert systems, and so on. Although there was no such a buzzword as AI. Isn't that, sir? Am I right? People used to talk about Simon Haykin neural networks a lot. And learning that book, Neural Networks by Simon Haykin, was a very admirable thing for students when I was studying especially. Well, that's basically the same thing we all do even now, although there is a small twist of the keywords. The science has advanced a little bit more. So I'll give a snapshot of the AI part towards the end. And I'm sure most of the contents will be familiar to you. So I have explained the word, why I'm using the word decoding. Is there any question on that? Why I am using the word decoding in my title? Is there a question on that? Are you comfortable asking questions? Or you want to be reserved, constrained? See, the main idea of a conference is to remove that restraint from people to be more free in communicating with others. Am I right? So especially the student community here, I would expect more of a response, either in Malayalam or English or whatever, to make this, the speech more lively, this lecture more lively. Because all my lectures are done interactively, although I do it for graduate students. So anyway, I hope you have understood decoding, brain aging, and then why I use AI powered, right? Which I will explain more elaborately, like expatiate on these things as I go through the slides. Well, I would love to have the laptop as early as possible so that, it's more comfortable for me. Okay. Here slides. So, by no means I have any financial interests. Oh, okay. Thank you. No means any financial interests or relationships to disclose. Other than I should, I don't know whether Dr. Shantini is here. I'm here mainly because of Dr. Shantini, because we had met at Norway and we had a lot of time together, my family, and she was there. So she actually asked me to make this presentation in such a short notice. Anyway, I thank Dr. Shantini and of course all other dignitaries of this conference. Yeah. So the main contents is understanding brain aging. That is the first idea, to give an introduction. Then age-related changes in the brain. That is the physiological age-related changes of the brain. Then quantifying the age-related changes. Then there is a brief introduction on morphometry. Then a little bit on quantitative MRI. And then finally coming to the idea of the concept of brain age. So the slide talks about understanding brain aging. So you can see in the picture, brain aging is a complex multifactorial process involving structural, cellular, and molecular changes. It is a major risk factor for neurodegenerative diseases like Alzheimer's and Parkinson's. So neurodegeneration means what? Degeneration of the neurons in the brain, right? So the reason for the neurodegeneration could be cellular, it could be molecular, or it could be structural, right? So I'm going to talk about all this. So this is, in fact, this lays the foundation or motivation of why we should study brain aging. So this is a motivational factor, because brain aging can be related to the clinical scenario, right? So what does the picture show? It shows a young brain, an aged brain. Then there are some abnormal lyosomes. Then the bottom part shows the normal aging. The other part shows the abnormal protein, synthesis in the brain that leads to neurodegeneration and dementia, because dementia is one of the leading causes. So because of dementia, there is cognitive impairment. The cognition is lost. That means I may not be able to, so if I have dementia, I may not be able to recognize my own friends or my own relatives, right? Which is very devastating, isn't it? Have you seen people with dementia, your maybe grandparents or close-knit people who had dementia? Yeah? So you know how devastating it is. And it is very lethal. It could even affect somebody's life. Now let's talk about age-related changes. So mostly there are two types of age-related changes: the morphological alterations. So what is morphological operations? If you consider the brain as a volume, the main component of the brain is the the cortical surface, isn't it? And it is separated from the cerebrospinal fluid through the PL surface. Little bit of neuroanatomy here, the fundamentals of it. So when I say morphological operations, if I consider a healthy brain versus a morphologically altered brain, you can see that there are minuscule changes of the volume in the cortical surface. So in later slides, I will define what is a cortical surface, right? But right now, we can just think of it as a surface with undulations. That means small expansions or small contractions in the surface. When I say small expansions and contractions, you could think of it as small hills and valleys. It's an undulated surface, and the normal surface also may be undulated. But when you compare it to the normal surface, right, with respect to the normal surface, there are slightly more perturbations, undulations, hills and valleys as compared to the normal surface. So these are called morphological changes. How do I go to any slide? Some login.
Or should I stay here?
Not necessarily.
Just increase the screen time so that the
Okay. Meanwhile, I have been on this slide. So, sorry, you skipped one slide. Can you go to the? Okay. So I talked about the morphological alterations, and there are the histological alterations. So you can see the microscopic alterations in the brain tissue structure, such as the neuronal loss, accumulation of abnormal proteins and minerals, and changes in the cellular organization. Of course, please don't think that, these are some vague slides. I'll tell you how to quantify this, at least very briefly, so that later on you can catch on to those methods. So let's talk about the morphological changes associated with brain aging. So you can see those numberings 1, 2, 3, 4. So for example, what's the difference between this slide and this slide? I can tell you is that on the left side, this is more of the, I would say, the white matter, right? And on this side, they talk more about the gray matter. So although it's not very clearly spelled out. So if you talk about the white matter regions, the major reason for morphological changes are demyelination, then it will be microbleeds, leukorrhosis, and lacunes and small vessel diseases. Whereas on the other regions, it's mainly because of ventricular enlargement. So you can see here the two brains shown here. As the brain gets older, even in the normal course, you can see that the volume of the ventricles enlarges, right? That's not a disease, but that's just because of your physical aging that happens, right? So we call this as cerebral atrophy. So the clinical side, people call this as cerebral atrophy. So ventricular enlargement, and then there is the cortical thinning, right? So when in the medical side, they say cortical thinning, what do engineers do? We do the simulations of the cortical surface using meshes and all that, triangular meshes, right? And we practically accurately measure how much of thinning has occurred. So there are ways and means of doing this. So yeah, so this slide talks mostly about the morphological changes. Now, what about the histological changes? So you can see that there are different histological stains. I don't know if you have heard about histopathology. In the clinical side, you might have noticed that there are medical physicians who are trained in pathology. They look at the microscopes, different stains, and so on, right? So I'm talking about those kinds of images. So the information that you gather from those images, right? The biopsies, right? So for example, if someone does a neurosurgery, they take samples of the tissue and they look at different stains. What do they look for actually? They look for mineral deposits. So minerals could be calcium or iron, right? As you age, you can see there are several theories, and people have proved that there are iron deposits. Ferritin. Ferritin is one of the minerals that gets deposited into the deep brain nuclei, especially the globus pallidus, basal ganglia regions. And there is the other extreme, calcification, right? Now, coming to the physics of it, what is the difference between calcium and iron in physics? Can someone say? It's a part of material science. So we know that ferrous materials are more paramagnetic, right? Whereas calcium is more diamagnetic. So when you talk about the susceptibility of that material, the susceptibility of calcium would be negative, right? Whereas the susceptibility of iron would be positive, right? So does it ring a bell in you how we can, utilize these, the physical concepts, can be married with the medical key symptoms that they see in medicine or the clinical practice, so that we can put applied physics into practice. This is what exactly people have done. So I'll show you in my later slides that there is a very interesting field called quantitative susceptibility mapping. Have you heard of this? QSM. QSM, quantitative susceptibility mapping. So this is part of quantitative MRI, where we can quantify, right, the amount of iron deposits, the amount of calcium deposits through electromagnetic calculations. Oh, that's very interesting, isn't it? Because we study a lot of electromagnetics. Where do we study electromagnetics in our engineering curriculum? For what? So I was speaking to some folks here just now, and they were telling me, some faculty members here work on microstrip antennas and so on. So that's mostly where we do electromagnetics, I suppose, right? Although I studied electromagnetics in great detail, I even do that now. And it has become so advantageous for me that I'm an engineer, that I'm able to apply these things into real practice in the case of neuroimaging. So, in a nutshell, what I've spoken about, what is the importance of this slide? The importance of this slide is that histopathology can reveal the different types of mineral deposits that occur, right, on the brain, either due to neurodegeneration or due to aging. Of course, aging means neurodegeneration. It's all tied up. But that doesn't mean a young person could as well get neurodegeneration, right? So that is why the concept of brain aging is important. For example, a person might be of my age and still that person's brain age could be equivalent to that of a normal, healthy adult with an age of 80 years. Why? Because the neurodegeneration has stepped in much earlier in that person, correct? So how do you know that neurodegeneration has stepped in earlier? because if you take the stains, the pathology and so on, you can see the mineral deposits, right? So you might ask me, how can we take the stains unless you poke the brain with something? They do that during neurosurgery, or during the COVID days, they used to take the, what is that, your CSF from the spine, the samples, and then you look at all these kinds of deposits, using biopsy. So this is the importance of histopathology, and that is also related to brain aging. So I've spoken about morphological and histopathological, what shall I say, supportive evidence, isn't it? Because these are quantifiable measures that you can achieve in the clinic. So essentially coming down to the concept of quantifying age-related changes through MRI, so that's where our focus is currently. We are not going to focus on histopathology or what else did I say? Mainly histopathology, which is a clinical tool. We are going to make use of MRI because MRI is an image, right? So we apply the image processing concepts through quantitative MRI techniques. So one branch of it is called morphometry. And of course, we can also apply quantitative MRI to predict, instead of, rather than poking the brain through invasive methods, you don't need to do that. Just from the MRI, you can predict what would be or what might be the histological variations. Isn't that good? That's very nice, isn't it? Because you don't have to go through surgery or any other methods. Just from MRI, you can actually assess those changes, right? So these are the current trends. So now let's talk a little bit about morphometry. So I've made little more notes to make this more appealing. As I said, I didn't get much time, so I have to refer to some of my own notes just to explain to you what this slide is about. So I have to spend 5 or 6 minutes on this slide because this is very closely related to computations, right? So how many people know what is a deformation field? Have you heard the word deformation field? Here is Dr. Shantini, the very cause of my coming here. So I have already, given my felicitation through our contacts at Norway. So thank you, Dr. Shantini. So yeah, so I was talking about the deformation field. So have you come across the word deformation field anywhere in your BTech courses? No idea? You've not heard? So people who do, I don't know, modeling. How many people do modeling here? Numerical modeling, fluid dynamics, whatever. Or have people used some kind of numerical methods somewhere? So those people should know what is a deformation field. So let's say you have 2 images, right? Always in neuroimaging, you have what is known as a template, right? So mostly people talk about the MNI space. That's a Montreal Neurological Institute. So they have established a template for normal, healthy people, right? So they've made brain atlases, which serve as a reference template. So whenever you get a second brain, let's say from a patient or from any other person, what they do is they normalize that image with the template. What do you mean normalize? Because this is a procedure often known as co-registration. So if you have two images, you can co-register the other image with this either through linear methods or through non-linear methods, which is known as non-linear warping, right? So if you have affine transformations, have you heard of affine transformations? Affine transformations, rotations, scaling, right? So when we study linear algebra, we have studied affine transformations, right? So if you co-register two images using affine transformations, how many parameters you get? You get 6 parameters for rotation, some for scaling, isn't it? So you get a fixed number of parameters that describes the whole transformation globally. That means for the whole image pair, for the whole two set of images, you can measure or characterize the transformation of one image to the other using a global set of parameters, right? You don't have to calculate the transformations on each voxel separately, right? If you compute the transformations on each voxel separately, voxel means pixel, right? MRI is a 3D image because our pixels are three-dimensional. So we have the in-plane and the thickness of the slice. So it's like a brick. So if you are computing the transformations of one image to the other, voxel-wise, or in a plain language, pixel-wise, then it becomes a non-linear transformations. For example, you can model the transformations using higher order polynomials, etc., etc. So the whole procedure under one umbrella, we call this as the process of registration, or co-registration, or in a simple language, we say normalization, right? So what did I say? For the morphometry, the first pre-processing that we need to do is to co-register or normalize the image to what? To a standard template, which is mostly the MNI template. Of course, there are other templates, right? But more popularly, people use the MNI template. So again, coming back to the deformation field, what is a deformation field? It is a vector field. And what does this vector field specify? That specifies how each voxel, which is a point in an image, like a pixel, should be moved physically to align with the other reference image. The reference image is your MNI template. So MNI has already, kept aside templates for different ages for normal brains. That is already available to you. It's given to you. It's a great service that the Montreal Neurological Institute has already done that work, right? And of course, there are other templates. These are also known as demons. There is, I don't know if you have worked in neuroimaging, there are demons called Tyler demons. A demon means what? A template. So I hope I have explained what is deformation field, right? So how do you characterize the deformation field? So if you have a brain, at each voxel, you will have a three-dimensional vector at each voxel that characterizes the deformation field. So why do you use this deformation field? Because you want to calculate some measures. What are the measures? As I said, compared to a normal brain surface, right? Aging brain might have slight deviations, undulations either hills or valleys, right? So in order to measure that, the local volume changes. That is the technical keyword for that. The local volume changes. You use the idea of the deformation field. Now, the next key idea that I need to talk about, which is very important here, is the idea of cortical surface, right? So what is a cortical surface? It is a mesh representation. So the moment I say mesh, many of the people, to them, it rings a bell. Can you wrap your head around this idea? Does it ring a bell when I say the moment mesh? Or are you trying to learn the ropes? I'm just trying to make some fun. Some people are smiling at me. What about others? Does it ring a bell to you? You're a BTech student, no? Yes? Yes or no? Yeah? Yeah. So do you feel interested in what I'm saying? All these deformation changes, how it is applied to the brain? It's very interesting. So a cortical surface can be computed as a mesh representation, right? What is a mesh representation? A surface, you represent it using a set of nodes, correct? That's it, a set of nodes, which is also known as a set of vertices. Now it rings the bell, right? Vertices. And then there is another technical keyword called phases. What is a phase? Suppose, for example, if you're considering triangular meshing, right? So you have three adjacent nodes which are nearby, and the area, right, that is represented or enclosed by these three nodes is like a triangle. So we call it, what do we call it? A triangular phase, right? And the whole process is called triangular meshing. So this is the key thing that they do here. So I'm coming to this point. This is the tipping point now. What is the tipping point of my presentation? Just to convey to you, because these are not taught in undergraduate or graduate courses, I wish to convey to you that these have practical significance in medical imaging, right? So these are applied. The body of knowledge that we learn is applied. So this way of representation in neuroimaging, it is called surface-based morphometry. So that is another keyword. So the measures that you get here, what are the measures from voxel-based morphometry? So I've defined what is voxel-based morphometry based on deformation fields, and the surface-based morphometry. Based on these two kinds of morphometries, you get these kind of measures. What are the measures? The surface area, the cortical thickness, the curvature, and the brain volume, right? So now you have a lot of features in the language of pattern recognition, and nowadays machine learning, we use the word features, isn't it? So from these images, we have these concepts of these features coming up from these measures. And what do these measures signify? They signify the structural changes or morphological changes, right? So on one side, we have the structural changes or the morphological changes that comes from these abstract measures. Do you agree? Yep. Now comes different from the structural changes. We have what is known as a big area, which is now coming under the radar for most of the clinical applications. This is called quantitative MRI, right? So these are two different branches, the structural changes and the quantitative MRI. So if you ask me, do doctors use this? Now doctors are becoming aware of this. Doctors in research, especially in Nimhan's, in the Indian scenario, they're learning this. But yet, these are not put into clinical practice. I should be very frank. It takes a couple of years for them to put this into the clinical practice. But they are heavily used in research, pharmaceutical journals. A lot of pharmaceutical grants come with this kind of research. And they have a lot of money, isn't it? So what is quantitative MRI? So quantitative MRI, yeah, of course, I'll be so happy to do that because I have to catch my train also. But it's very unfortunate that I have to finish it because of this time constraint, because, it was just squeezed. Timing was squeezed. But I'm very sorry. But the moments I spent with you, I think you've relished and had the opportunity to gather a lot of keywords and what they mean. This was my whole idea, to introduce these keywords to young people, so in future, they can chase this research, which is a very growing field of research in the area of imaging. Yeah. So let me come to the key slide. I'm sorry to, again, I'm leaving these slides here for your reference. So there are several quantitative MRI methodologies. As I said, the most attractive of them is quantitative susceptibility mapping, proton density, magnetization transfer ratio, fractional anisotropy, mean diffusivity, oxygen extraction fraction, which is becoming, our lab is the first lab in India, to be very frank with you. I'm not blowing my own trumpet. Our lab is the first lab in India to have computed oxygen extraction fraction. And the first PhD student and my last PhD student who has done that. And it got published in medical physics. So we are the only people in India who have computed oxygen extraction fraction. And we have done all these experiments in Nimans. We got all the data and we computed that. And we sent it to the people who first computed oxygen extraction fraction in some other university. I don't want to name the university now. So that's one of the important area. And we also work on myelin water fraction for the white matter. We have, all these fancy methods, what you apply to the antennas. We have applied for the myelin water fraction, the method called matrix pencil method, which is very common. We have applied that to myelin water fraction. So there are, lot of overlapping things between electrical engineering and this particular area of neuroimaging. And then very lately, we have been able to, with multi-compartment modeling, we have come up with this new measure of cerebrospinal fluid fraction, CSF fraction. That was another key measure that we have come up with in quantitative MRI. So where is this all leading to? That's the most pivotal part of this talk. So this is about QSM, quantitative susceptibility mapping, where we model the dipoles in the brain, the magnetic dipoles, right, through inverse models. So we do inverse modeling and we extract the magnetic dipoles in the brain. And with that, we are able to measure the magnetic susceptibility. And of course, this is very common. We measure the transverse relaxation rates using multiple echoes from MRI. So we call this as the R2 star. And its unit is in hertz, just like our power line frequency. So we have 0 to 50 hertz for the transverse relaxation rate. So these are all quantitative measurements. And of course, we have this cerebrospinal fluid fraction, which comes from a multi-compartment model. Now, again, I don't have the time to explain all this, but of course, the slides are available to you. And of course, feedback etc., can be done at a later time. And with all this, we have done the normative trajectories of all these quantitative parameters. So it tells you with age, how do these measures change, right? So if you see the regression of this cloud points, you can see the mean curves of how the parameters vary with age in a normal brain, not in a pathological brain. That's very important. Now, this is some of the high resolution quantitative MRI that we did in the lab. And all the biophysical models, the quantitative BOLD model. BOLD means blood oxygenation level dependent model. So we are able to get, mappings of oxygen extraction fraction and the relaxation rates from the model, the tissue relaxation rate from the model. Here comes the unsupervised clustering. So we have seen that this is one application where we used unsupervised clustering. And the purpose and application reduces the data complexity while preserving the tissue behavior and enhances interpretability of quantitative MRI features across different regions. So this is the first instance we were able to apply artificial intelligence in a very primitive way for this neuroimaging application. So we have classified it as metabolic signatures by dividing the regimes of the signatures for getting meaningful maps that correlate with aging. So you can see in the next slide how these meaningful maps are obtained. Can you see the difference of the iron depositions that we have been able to map on the basal ganglia? As the normal aging goes higher, what do you see? So in a technical keyword, I should say, the mappings becomes sparse to denser. Can you see that? Sparse means what? Like dots, right? But as the aging goes high, you can clearly see that the mappings become more dense. That is why you see the rich red patches, right, which are more dense as compared to the young ages. So now we have at least come up with a quantitative measure that is related to brain aging. Of course, we have used unsupervised clustering to get this. So that's the key part, right? Tipping point. So now the next idea that we have is, why not we think of a comprehensive measure, right? A unique comprehensive measure. So when you talk about AI, how do you get a unique comprehensive measure from your networks? You use the, what do you call, the MLPs, right? So the very end of your network, use MLPs and some kind of gating is applied. By the way, I am myself a coder. I do coding. I do AI myself, right? I am passionate about this very lately. I've started this just after I retired from my service. So I'm very passionate about coding in Python, TensorFlow, PyTorch. It has become a favorite. I don't know. I'm very excited to say that it has become. I used to use MATLAB, but now I'm very fond of Python. It's very handy. So I make very big complex network stages for other applications in MRI, not just clinical, just for your awareness. So yeah, so anyway, to wrap the talk, I would just conclude by showing you this slide, how we are able to come up with a deep network to quantify the brain age. So we have used two encoders, quantitative MRI and the feature extraction. And then we use tokenizations, right? Tokenization which remember the spatial encodings of the image. And then it goes to a self-attention, like in a transformer, multi-head stages of self-attention. And then finally, we apply some bias correction, because there is always a bias in our calculations, and we use this EBRIM data set, Advanced Brain Imaging on Aging and Memory data set, as described in this paper. So these are some of our results. This is the population statistics that we used for our deep network. Well, this was the kind of architecture that we used. Two encoders, separate encoders, one for the structural part, the other for the quantitative part, and then combining the features using a transformer. And then our reference was the normal brain age, because we use normal patients, right? So in principle, we assume that the brain age should be same as the chronological age, right? But actually it doesn't. So when the network converges, we always get a difference from the actual age and the brain age. So this is the results that we got. So what is that figure that you see? This is one of the key results that we got. So you can see on the y-axis, we have the age difference, the pathological age difference, which is the difference between the normal and the brain age. So you can see that for young patients, for young volunteers, it is positive. And as it goes to the aged, there is a negative dip. So there is always a bias in our calculations. And once we correct the bias, the regression becomes a straight line. There are no errors. So that is why I showed a bias correction. So anyway, I don't want to prolong much, because I have given you a glimpse of what this field is about. As I said, to summarize, the whole idea of my presenting this topic to you is one, right? In my the previous small talk that I gave you, I gave the students a glimpse of today's what is that called? The career tracks are mostly based on startups, right? People are looking for startups everywhere. That's the first thing. And the second thing that I want to be assertive about, very, very important from what I feel to share with even senior people, professors and all that, my experience is that the era of classical teaching has died down. It is fading away. Now, people are very much aware of the courses themselves. I don't know. People are so different. The young people are so different from what we were nowadays, because there are many resources on the internet, ChatGPT and so on. Self-study becomes very popular now. In this instance, our education is now transforming into a new era, and I would call this demand-based courses. So if someone asks me, hey, what do you teach? I would say that depends on the demand, right? And people can learn it in just 6 months, a very rigorous course. I do that in my institution, right? People come, register for the course, 6 months, the demand-based course, and they get the training and they get placed, or they go into a startup. So this is the whole idea. So I wish to share my experience that this transformation is where we are heading to. And I think this technical conferences should also highlight this key aspect. And with that, I conclude my talk. And again, thank you so much for your patient listening. Thank you.
So, for the interest of the time, we will have the question and answer session with the lunch. We'll move on to the next.
Yeah. Correct time, 1 o'clock.
Please get the third option. It's a token of appreciation, certificate. PPT ആയില്ല.
Sorry, I'm not able to take part because of my trade. Yeah. So all successful.
Thank you. Thank you. I'll keep a timer for my talk. Okay. Good afternoon to everyone, and thank you for the organizer for inviting me for this event. I'm very happy to be here, and as I'm also an alumni, I know that I'm not coming here as an alumnus, but as a speaker, that gives me extra happiness. So I'm going to talk about a topic: mathematics, computation, and AI. I was talking to Dr. Shahin sir. He said all the students here are very good in math. So you can ask, all the questions are aiming to only the students here, okay? So I'm challenging him. Some will be very easy questions, don't worry. We have heard from all the speakers, we are living in an extraordinary time. Now machines can predict market behavior. It can translate language. And it can scan image, diagnose diseases. Do you know that we use the same technique for identifying damages in an aircraft? The same technique, what you use it in diagnosing disease. So we package all this as something called artificial intelligence or AI. So do you think AIS is a new technology, just came out in vacuum? No. So I think you are in agreement with me. That's what I'm trying to show here. It is actually a long journey, intellectual journey since ancient times. And I'm not going to take you through the historical aspects, but the conceptual part of it. This is what I do at Kuwait Institute for Scientific Research. We do monitoring of several infrastructures. Actually, one of the tallest concrete sculptured tower in the world, actually. And we are also monitoring a highway bridge and wind turbine and a couple of other infrastructures. If I have time, I'll go through this. And I would like to start with this. God used beautiful mathematics in creating this world. I know many of you will disagree, so I cross the word God. So you can replace it with whatever you feel, maybe nature or God, whatever fits with you. Actually, this is not a very simple word. You can see that this is actually woven into the fabric of nature. Let me give you a very simple example. When you listen to my speech, whatever it is going through your ear, are you all good at Fourier transform? Signal processing? What do you do? What is the concept of Fourier transform? We break complex mathematical functions or signals into simple pieces of sines and cosines of various frequencies. Do you know that our ear is exactly similar to a Fourier filtering?
Our inner ear has what is known as a cochlea. It contains thousands of tiny hairs. Do you know what it is for? All these vibrates respond to different frequencies. So what happens when you listen to a music or recognize a voice when the sound reaches our inner ear, it vibrates fluid inside that actually activates certain portion of this inner ear with various frequencies. It is exactly like you break a complex signal into various frequencies. This is just not a coincidence. It's actually a just simple glimpse of an example how mathematics is tightly woven in the fabric of nature or in our life. By the way, he is also an electrical engineer. He's very famous. Who is he? Quantum physicist, but he's actually an electrical engineer by education. Later, he moved on to. No, this is my favorite slide. Have you seen anything similar to this recently in the news? B-2 bomber, you heard, right? Were you closely watching this war, Iran-Israel? Because I come from that side, from Kuwait. You might have seen how the B-2 bomber was dropped. So this was my first project while I was working at ADA. This is an external fuel tank for the light combat aircraft, LCA, where after the fuel is used, the mission is over, they drop and go. So to design such a structure, you have no prior experience. You can't go and test it just like that. Where do the confidence come from? It's purely from mathematical modeling, right? So I'll share one more experience, while I was working in GE, General Electric, whenever we design new turbines, it need not be completely new. Even if we change a blade, we used to, before selling into a new client, these new turbines, we have to do a complete full-scale testing after all rigorous review and design process. But what happened lately, that was 10 years ago, we were so confident that our mathematical modeling predictions are so accurate with full scale, we completely eliminated and we saved millions of dollars. So that's the confidence we had in computational modeling. This is happened very recently, I think a year ago. They moved a building in China completely into a different place. They did not demolish. This wouldn't be possible if you did not have the confidence in our mathematical models. Now, what happens if you make an error? You might have recently seen a flight completely collapsed, right? And many of the analysis, you see that there was not enough lift, isn't it? It is a very simple equation what you studied in first year engineering mechanics. Do you remember the vertical force equilibrium? Do you remember? Anyway, now the mathematics, of course, this particular incident was not a mathematical error because it has been running for many years. So that is nothing to do with, but what I would like to share, if you make any error in mathematical modeling, it can also cause very significant, it could be very costly. This is the Tacoma Bridge. Have you heard of Tacoma Bridge? Very famous. This is a bridge, a hanging bridge, which was designed in 1914 Washington. And then it was a very well celebrated bridge. And the design was done by all the standard practices and all the sophisticated method and design practices, all the tests they could do. And in fact, it was claimed that it is designed for a wind speed of 40 miles per hour. That's approximately around 60 to 65 kilometers per hour. But what happened? This bridge failed after 3 months for a wind against 30 kilometers per hour. That was very interesting. What happens when we design when civil engineers design bridges? Dr. Narayanan is here. He knows that when we design any bridges or a building, because building and bridges undergo vibrations, right? A vehicle passing over the building, or a bridge, it vibrates. So what is known as, whatever you know that in the FFT, Fourier transform, you find out the frequency content, right? Here, what we do is we avoid resonance, or one of the simple phenomenon is we avoid the resonance phenomenon here. But in this particular case, there is another phenomenon which we civil engineer never considered. That is not a stability problem. Maybe electrical engineer know more about it. If you have an eigenvalue problem, there is something called a stability problem. What happens? You can see this. This is the time response analysis results. As the time passes, if you oscillate a pendulum, what happens after some time? It dies down, right? Vibration comes to a rest. Why? Damping, right? Where is the damping coming from? The air, right? There is a very interesting phenomenon that happens. Any structure vibrates in a moving air at a particular speed of vibration, and the air speed, the air, instead of acting against the motion of the structure, it actually feeds this energy into the system. So instead of the amplitude of vibration going down, it actually goes up, which we consider in an aircraft structure. Usually we thought, okay, this is a phenomenon when a light structure comes into contact with a flowing air. This is a very important phenomenon when we consider the vibration of aircraft wing. But we thought that the bridges does not have this issue, and that was not at all a consideration. And this bridge, this was a light structure. When it came to a flowing wind, this underwent a flutter, what is the stability issue, and it collapsed. So it was a purely mathematical error. And in fact, this failed after 3 months of construction. This is a couple of charts for the flutter results. Now, I would like to start the core of my talk, that, humans have been trying to model the world around us, either through the abstract math or whatever tools we have. So one of the first is, I think I would consider as Archimedes. The first equation, you all know that this is the law of lever, right? There is a famous quote. What is that? Give me a long enough stick, I will move the earth. That comes from this equation, this simple equation. And mechanical engineers know that this is one of the most fundamental equations in fluid dynamics even today. And he derived when was Archimedes lived? I think 200 BC, that's 2,200 years ago. It's not only here, he did something interesting. The Greeks were quite good in geometries, especially straight-sided. But when they come to curved sides, they were not very good. For example, calculating an area. What is the area of a circle? Pi r square, right? What is pi? What is pi? What is pi? It's actually the ratio of a circle perimeter to its diameter, and you get a constant. How big or small the circle is. And they knew for a long time. And they tried to solve this problem. Most of the time what they did is they measured the perimeter, they measured the diameter, they made several circles. And throughout the ancient times, they made several circles, they measured the area, the perimeter, and they measured the diameter, they divided it and calculated the average, and they found value of pi. This was in an Egyptian book by 3,600 years ago, very close to, he gave an equivalent area of a circle and square that approximate pi as 3.16. It's a remarkable accuracy. But Archimedes was the first one who proposed a method analytically, because they were quite good at straight lines. He said, I don't have to know, I can approximate this, I don't have to know the curved one. He approximated with a straight-sided polygon. And he was able to approximate, he calculated the value of pi to an accuracy of 3.14. So people have been trying to model the world around the problem to their tools they have. One of the first thing people started is the average. How do you calculate if you have a set of numbers? Let's say I have a vector C of I. How do you calculate? The sum of each element divided by the number, right? We all studied in our 6th grade or 4th grade. Is it a definition? Or is there a mathematical basis for this? Have you ever seen a proof for this? Is it a definition or is there a mathematical basis? I'll show you something very interesting. This is an outcome of the very similar equation what we use in basic AI. Suppose you have a set of numbers, C of I, and if you want to make a best guess out of all, let's say A, and if you calculate the error, square of the errors, and you have seen in least square regression, right? You do this similarly, right? If you define S and if you do ds by dA, you get the result of an average. A is equal to 1 by n C of I. I'll show you something more interesting. Have you seen vectors? You had the vectors class, right? Vector algebra. You know, this is the geometrical interpretation of this average. If C is a vector, C of I, and A is a vector, all elements are constant A, you can do in Excel, once you go back home, you can create very easily. Calculate the error S is equal to C minus A, calculate the dot product of the error S and A. It will go to 0. You can do that, right? That's a 1 minute job. You can calculate the dot product. I think it's quite easy, very straightforward. So A, average is an orthogonal projection of your measurement, and this we have been doing in ancient times. In ancient times, I told you, when they want to solve a very simple problem of pi, they make measurements, and they realize somehow they did not use this rigorous math. Somehow they came up with the average, and for example, astronomy, the cycles of moon, they measure it. They measure the number of cycles, 30, 29, 30, 29, and they came up with average. And in several other cases, and the beauty is, it is coming as a minimization. Now, what happened over the period of time? All the several scientists, for example, Newton, he wanted to describe the world more accurately. He discovered what? What did he discover in math? Calculus, right? So he started describing the world around us using differential equations. So what is the differential? What is the differential equation? When does it come? That means the system around us, he modeled as a continuous system. It is no more a discrete, right? It's a differential equation. The solution is a function, right? It is not a number, right? Previously, I was giving C of I numbers. Now, when he described the world around us, the system, the solutions are functions. Now, what happened? Over the period of time, we wanted to model the world around us more accurately. What happened when I have a complex differential equations? What is the difficulty? What happens if you have a very complex boundary conditions? Pardon? It is unsolvable. So most of the real things around us cannot solve. For a simple example, have you seen this? What is the right picture? A building vibrates under an earthquake or a wind, right? You have seen this video, the second one, right? Isn't it? Right? Do you know that the entire tower or the catching arm can be described? The first the differential equation what is shown here. And if you go back to your, I don't know, you studied this Euler-Bernoulli beam formula. This is the very basic differential equation which we use to describe both problem. That's a very basic. And if you slightly complicate, you might have seen Euler-Bernoulli. We neglect the shear strain. Actually, the dV by dx minus theta, we neglect it. That means they equal. That term goes to 0. That's how it converges to this. The moment we relax that assumption, the differential equation becomes more complex. And if you bring in 2-dimensional, 3-dimensional, there is no solution. Now again, we had to solve this. Now in early 20th century and all through until recently, we have started developing, we have again made it discretization. We started discretizing our continuous system. That's how we developed the entire matrix algebra. And of course, there are a few things came up in, we wanted to bring in the uncertainties, probabilities theories were developed. And one of the, so the only way to solve this unsolvable system is you have to approximate it. One of the, you can see that this is actually the first equation is vibration of a bridge or vibration of an aircraft, and all of you are familiar about this equation, right? Isn't it? Right? This RLC circuit. Do you know that this is the same equation? Anyway, in simple physical system, there is a solution. But when it becomes complicated, for example, if you want to model this, there is no way. Right? You have a very accurate, everybody says you wear a seat belt. Do you know where it is designed? Do you know how tight? How tightly, what is the elasticity? It is coming from this model. And do you know that that was the same differential equation I showed? So the only way to solve this unsolvable is to discretize an approximate solution. In fact, as I mentioned, the first few slides, how complex structures, physical systems we design mostly from the numerical models. So if I want to test a car in a crash, they cannot burn hundreds of cars. So what they do model thousands. If they want to do 1,000, they do 10. This is an approximate number on experiment, and they benchmark with your numerical model. Then the later they do on the numerical experiment. I'm sure that once the time progress, they even stop even the 10 testing. I told you in GE, we don't do a complete full-scale testing. We completely depend on the model. So it's so accurate. Though we say it is approximate, I wanted to tell you this. It is actually not approximate. It is better than the exact, the approximate solution. But now, how do we solve this? It's very simple. I think those who have done finite element, if this is our exact differential equation and U is an exact solution for this, right? This is a very simple, the very basic differential equation which you have studied in your first year engineering. This is the first differential equation, you solved it. Actually, now you can actually solve this by integration. Now, if you want to do an approximate solution, I approximate with an approximate function UH. So, naturally, you don't get it 0, right? There is some error. That's exactly what we do. This is some mathematical treatment, you know, the weak formulation. I don't want to go, we can do this. This is a simple integration by parts. If you do a simple integration here by parts, you come up with this. Yes. So, basically, we do an error minimization, and what happens is, if you do all those methods, this is actually a paper from my own paper. This is actually my own work, has been published. What you see is, you get a very beautiful orthogonality condition. That means the error in your approximate solution is orthogonal to the approximate solution, exactly what we have seen. The average was orthogonal to the error in the average. And this is a bit complex because it is in a vector, it is a function space. Here, everything is a continuous, all are functions, not this dot product, all the dot product, everything are same. Similar, but all these are continuous functions. Now, the approximate solution method, what we call finite element, is not only, though I use the example as finite element, I have also showed for finite difference method and various classes of differential equation. It satisfies this beautiful orthogonality condition where this is the approximate solution, that is the exact solution. And if you calculate the dot product of the error to the approximate, it vanishes. And something I very interestingly I derived, I like it. This was one of my first paper, the energy of the error equal to error of the energy. Anyway, it is not relevant here. In short, we have used the same similar equation even in our computational model, what was used in ancient times. Now, this is an extension of my work on an eigenvalue problem, and it becomes a slightly complicated. I have shown that can be interpreted as a frequency error hyperboloid. Maybe those who are in machine learning, they might have, by the way, in machine learning, if it is not orthogonal, you can actually calculate the angle of those two vectors, epsilon and epsilon h. That's actually, it will show you how much it is deviated. Machine learning people, they use as an error indicator for sign similarity. I have used it for nothing to do with machine learning, simply for an eigenvalue approximate solution. Very recently, I just wanted to tell you, just a coincidence, I just got a paper to review. After our Lok Sabha election, somebody did an analysis. He wanted to analyze how different sects of different groups of people, castes or whatever you can call, how they influence the voting pattern. That's from the survey results, and he used cosine similarity as the indicator. That's very interesting. Anyway, now we have seen the error minimization is not a simple concept. It has been used in ancient time even to calculate the average. Then over the time, we have used one of the most used method across the computation models, the minimization of error. And when it comes to AI, we use the same concept and the same equation. Here, what happens? Here, you have the measured data. Here, there is a slight difference. All these days, what happened? We have understood the physics of the system, and we describe the system, and we have the mathematical model, and then we predict using this equation. In this case, we don't know anything about the system. We have the input and output. Using the input and output, we predict the behavior of the system. Sometimes, I will tell you its disadvantages. In this case, we actually minimize the error, the predicted versus the measured. And if you look at is yi is your actual measurement, and f of x theta is your prediction, and theta is some constants. We minimize this such and find out the values of theta minimizes this error. In many cases, it's exactly the L2 norm squared, what I have showed you, even the average, even the computational model. Slightly it can be different. What is interesting is here it may not be in many complex system, you don't get a perfect orthogonality condition, but still you can calculate the deviation of, but they minimize this error. I think I will, I think my target. So now, using this, 2 years ago, I visited Arizona, Tempe. I saw that cars going all around with this something rounding on the top. Not now, 2 years ago. And interestingly, I realized there is no drivers. And just like any other car, the frequency of the numbers of car is just like any other car and going all around. People are getting dropped. Where do the confidence come from? The mathematical accuracy, our mathematical rigor. Does that mean? Is it there? Everything, as I told you, is just a minimization of error. That means there is a scope for error. I'll show you, you will be surprised. Though we have a confidence to go for a driverless car. Anyway, it can do something. This is actually a picture of my daughter, my younger daughter. I'll just tell you something human cannot recognize. The hidden math. So all of you know, right? If you read an image, it is just a matrix, right? It can be a two-dimensional or three-dimensional matrix, whether it's color or colored picture or black and white, isn't it? So that means the nose is defined by a group of numbers. It could be I and you are different with some average, some form of averaging, some form of statistical single number, right? And that's exactly AI recognizes. So whenever I go with my children, together with my family, I have two daughters, Rima and Ria. Whenever we visit friends, most of the friends say, my elder daughter looks like me, and my younger one looks like Sana, my wife. But AI told me the other way around. My elder one looks like exactly like Sana. Can you guess? How did I find out? I think it's an easy guess. How do you unlock your mobile? Right? We put a very beautiful password, right? Face recognition. We thought that it's so personal, right? So Sana's mobile, not she, my elder one, can unlock so easily. So it was initially she thought an accident. Then she did a thought experiment. Then we realized, oh, she can actually unlock. So I am telling you, it's not a story. 95%, if not more, tells all my friends and relatives, she looks like me, and the younger one looks like what? They told me, AI told me that it is simply the mathematical features. What is the hidden pattern we cannot see? Right? I'll tell you another example. I had a Chinese visitor 2 months ago, and he told me, when I visited before 4 months ago China, I couldn't recognize each one of them. It's just like ants, if you go ants, can you recognize two ants? Right? Same ant, right? Isn't it? So I felt, no, I cannot recognize two Chinese. But I thought that I can recognize Naran and Sajish, all of them very easily. So I took him to several meetings. It was a very crash 1 week visit, okay? So I had to take different clients, different collaborators, several meetings. Then at the 4th day, he asked me, Jafar, did we meet this person? And he said, I cannot recognize anyone. So I realized, oh, this is how we train. It's all about the training model where we are trained. They can identify Chinese so easily. That's how they are trained and tested. We can identify all of us, right? If you are anytime visit, is my time up? I think yes, maybe in 5 minutes. I am 31 minutes now. I want to stop quickly. So, as I told you, we think AI is so beautiful, but it can also so stupid things. Tell me which is bigger. If I tell 9.11, will you listen to any of thing what I told you? Right? You will know this guy is crazy, right? If I tell you today, now it's afternoon, you'll say no. It is going to be night because he's saying 9.11 is bigger. This is what ChatGPT told me. And I'm not surprised. Why? There is a scope for error. As long as your model meets your error requirements, it is good, isn't it? Those who are in AI, and this is an 8th grade problem. For my daughter, I asked ChatGPT, and it was even, so in the previous case, it just told me this is bigger. It didn't tell me the reason. Right? I did not have the courage to ask, which is why 9.11 is bigger than 9.9. But here it gave me a beautiful proof. But this was totally wrong. And I'm not surprised. Why? Again, it's a math model and it is all accurate, certain bounds, right? Now you can see that the similarity from ancient time, we use the error minimization, and if you want to solve the the computation model, use the same equation L2 norm, and we use the very same equation even for AI. Now, what has changed now? Why did AI took it up? This space of modeling, mathematical modeling. Now we are actually depending. I can tell you it is so accurate. Though I said this 9.1, I can tell you from my experience, it can really see hidden pattern which we cannot see. No physical attribute. I just told you. How do we recognize, differentiate different people, right, my daughter? And that is actually true. Because when we have research just published, actually yesterday it got published on our paper, unsupervised machine learning. I have no idea those indicators which I use to identify the damages, I cannot physically relate. It's just some matrix, some mathematical, some parameters. I cannot correlate. Only thing is I have to check. Oh, it says correct. Is it correct? So what did it change drastically? If you look at, there are three components in AI in general. One is very high quality data, right? And the second thing is very robust algorithm. And the third one is the computational power, isn't it? Everything has been changed recently. I'll tell you an example. While I was working for the LCA, I used to do monitoring of the fighter jet. Okay, I was part of the stress group. I was the one responsible for, this was the drop tank was my first project, and I was the first one to do the monitoring there. We just started. I still remember we had two sensors at the wing and the main fuselage frame connections. I had only two screens. And I go to the pilot in front before the flight. I ask him, can you do a rolling? Because there are specific, you have seen, right, in the fighter jet. Have you ever seen an air show? It rolls, it drops. It's like, do you watch soccer? Soccer? Do you know how Messi breaks the inertia, law of inertia? He turns on one side, he stops, everybody moves. He doesn't have any inertia, right? So the fighter jet has to have this maneuverability. So anyway, I used to ask the pilot to do certain maneuver, and I used to collect the data post-flight, not in real time. Do you know how many data points I collect? I have two sensors, I told you. I collect one data point in every 5 minutes. Now, do you know what is the measurements, what I do in a building? Those days, monitoring is done only in aircraft structures and very complex structures of mechanical component power systems, never ever for buildings and bridges. Now, even for a building, do you know what is my measurement frequency? I have hundreds of sensors. My measurement frequency is more than 1,000. Recently, we have also did for 10,000 samples per second from one sensor. And I have hundreds of such sensors. And it is so cheap. So we have our mobiles, satellite data, everything is data. The data, we have very high quality data. That is the first reason it changed. Number two is algorithm. Algorithm is changing rapidly. Do you know that now everybody knows about AI, right? Isn't it? Why? Why? ChatGPT, isn't it? This is after ChatGPT, the AI has changed. I think I'm overshooting my time, 37 minutes. After ChatGPT, it has become a general purpose tool, just like internet. Even the normal people started using, as I told you, we were using this AI for a long time, similar to the models, the math models. But after ChatGPT, it has changed. Now, how did ChatGPT change? Until 2017, it was just a paper, what is known as a transformer model. Just by one paper, we were able to train a large model from Google. There was a paper came, attention all you need, you can check it. Attention all you need is a transformer model. It changed the value of AI among the public. We were able to train a large amount of data and general purpose model like large language model. Now, when you talk about AI, previously AI means predictions, right? You have an input and output, you predict your output for an unknown output data. If you have any input, you can predict it. But after ChatGPT, after this transformer model, we were able to make general purpose model. Now, when we say AI, in general, it is a generative AI. That's a next form of large language model where you have video content, you can create audio contents. So that's a whole form of generative AI, but the base. So there is a huge change in the algorithm. And the third, definitely computation power. I used to work at NA, National Aerospace Laboratories. It is known as, the division is known as Center for Mathematical Modeling and Computer Simulation. You know, we used to be the largest powerhouse of the country. And even today, even now, that institute has been changed, Fourth Paradigm Institute, the largest computer those days. And now, recently, I was listening to NVIDIA CEO and Microsoft CEO, just I think a week ago. He said, in the last 2 years, between them, they just created a computational server which is 40 times more power what they did it in the 2 years ago. That's, you're talking about the 40 and from the highest. That's the way it is moving. Now, this slide is done by my research associate. He is actually doing a PhD. So now, does that mean the AI can will go exactly like this? It can. Can you just depend on the data and the output? Do you all use ChatGPT? Yes. Do you use it for solving your problems or what? Yes, very good. Did anybody, anytime, tell me, if you ask any question, did ChatGPT tell you that I don't know? Right? Do you know why? That's a problem with the self-driving cars and aircraft. It has the arrogance of ignorance. Now, that means you cannot depend completely from the data alone. Now, what is known as coming up is, especially this is an issue for risks that we cannot tolerate. Now, we have, this is like, see, in general, the general purpose AI is an unconstrained optimization problem. But when it comes to issues like this, you have to have a constraint. You have to have the risk. I think I am very much there. And there are a couple of things I think it will change. Now it is going for physics informed. Okay, let me just, the other thing is on the explainability. See, you have I think somebody was showing you these are the features what extracted. But do you know that AI model can never tell you a sensitivity parameters? It can, but the explainability is very low, especially for complex system. Right? If I show you a differential equation, I showed you the RLC circuit equation, right? I know that what happens exactly, right? How the system is going to behave, but in AI model, no way. The explainability is very low. And the other thing is the generalizability. Now, what is the solution? I think going forward, it cannot be only data. We also have to enforce some physics, right? Let me give you a very simple example. This is a work which we did, physics informed machine learning. This is one of the, but in general, the constraint and unconstrained optimization. So if I want to predict a matrix like this is actually the problem of your RLC circuit, where the right-hand side is 0, it's a homogeneous equation. You remember your complementary function? How do you solve such equation? You have a complementary function plus. See, he is better than all of you. So very nice, yes. So this is, anyway, if I want to do a complete prediction of the system, at the end of the day, this is a matrix. So what happens? AI has to predict all the entire matrix. But he knows that from the physics of the definition of this problem, this matrix has to be symmetric. So I can put a constraint. You don't have to tell me if we can enforce such physics, non-physical phenomenon or mathematical character. I think with this I'll stop. I have taken 43 minutes. If you have I think 1.5 minutes question time. I hope, by the way, I hope it was a very difficult topic to present. So thank you very much. And I thank Dr. Sajish for inviting me and giving me an opportunity. It is very happy to meet all of you, Dr. Shahin sir, Dr. Jayaprakash, Dr. Narayanan, and all of you. And nice to be here. Thank you. If you have any question, you have 1 minute. Or any comment. This is, I tried to put some thoughts, what I had. Yes, yes, yes. I think this one seems to be some failure in the control system. Looks like it's a very drastic failure. Yeah, I think it is very unlikely to be any. Yeah. Yes. Yeah. By the way, if you look at an aircraft design, I was in an aircraft industry. Do you know that just because of the shape, do you think an engine pushes up the aircraft? Right? What does an engine do? Tell me. An engine pushes just like a car. That means forward. It never pushes up. What pushes up? You will be surprised. Just to the shape of the wing. That is how we optimize our airfoil section. If you cut, so just for the shape of the wing, when it goes on a certain speed, it generates a lift. So when the lift goes more than the weight, it goes up. But in this case, looks like it was a free drop. Definitely the lift it did not generate enough lift. I don't know why it did not generate. Looks like engine failure. I have no idea. I don't want to propagate, but it's a very simple. It couldn't generate from the seemingly the explanation. It couldn't generate the lift. But just I want to tell you, the lift actually coming just from the airfoil section. Yeah, I think with that we can conclude. Then I think I'm perfectly on 45 minutes. Okay, thank you very much. And again, thank you for the organizer. I'm really happy.
Sir, I never thought that.
Let me take a photograph of one of the city. Those who want to contact,
Hello. So it's lunchtime. We can disperse.
നിങ്ങളുടെ വേറെ സെഷൻ